You know, the bad thing about lecturing at the blackboard is, and I have this special, there's this special, do you know about Hagamoro full touch chalk? This is a special chalk made in Japan, and it has a little plastic coating around the outside of the chalk, so that when you hold it, the chalk doesn't get on you so much, and then as you know, it rubs away. But eventually, you're covered with chalk anyway, so also they went out of business, but I think you might still be able to get it on Amazon, I'm not sure. Anyway, we're supposed to be talking about the modular J function, and to start, let me notice that at weight 12, it's the first place where there are two independent modular forms of this weight, and 12 is equal to 6 times 2, but it's also equal to 4 times 3. So E6 squared and E4 cubed are two independent modular forms of weight 12. Well, I guess it could be that they were somehow the same, but you know, we have formulas for these things, and so you can work out what they are. And they're clearly not the same. So in particular, you can do something interesting, which is to cancel off the leading term and define a weight 12 form, which is the combination E4 cubed minus E6 squared. And if I take this minus this, the coefficient of Q is 1728. But rather remarkably, if you divide by 1728 to make that leading coefficient 1, all the remaining coefficients of this form are actually integer. And the coefficients of this are historically denoted by tau of n, q to the n. This tau and the tau in q equals e to the 2 pi I tau have nothing to do with each other. This name, I think, comes from some German word that starts with T and then got turned into a tau. But it's historical, but anyway, so don't confuse the two taus. So this form has the special property that delta goes to 0 as tau goes to I infinity, because we've killed the constant term by canceling it. The leading behavior goes like Q, and Q goes to 0 as tau goes to I infinity. A form which does this is called a cusp form. A cusp form, I guess because it sort of is well behaved, it doesn't blow up, it doesn't have a pole. It goes to, well, sorry, it's not that it doesn't have a pole, it's that it actually goes to 0 as you go to the cusp at infinity. Now, we can make something of weight 0 by dividing two weight 12 forms, and if you divide two weight forms where one of them in the denominator is this weight 12 cusp form, you get something that's called J of tau, and because delta goes like Q as you go to I infinity, and E4 cubed goes like 1, the leading term here is Q to the minus 1, so this has a pole. at I infinity, and therefore is not holomorphic, but it's an example of a weakly holomorphic form. And the next coefficients are these. So since this is weight 0, it satisfies a very simple transformation law. It's just invariant under modular transformations. And sometimes people define capital J of tau to be J of tau minus 744, which is also weight 0, because, well, a constant is modular invariant, and so you can add or subtract constants if you're at weight 0. Now, people generally just do this and say, well, okay, isn't this nice? And now we've got a weight 0 form. But you could ask a question. Why don't we consider the same thing where we take some other ratio of weight 2 forms? Why not do that? Well, you could. And the formula that I gave before and was discussing with a few people shows you that E4 has a 0 at omega, E6 has a 0 at I, and so taking these ratios does give you a weight 0 function, but it gives you a function that has a pole in the interior rather than at I infinity. And you can consider such things, but doesn't quite fit into the definition I gave you of weakly holomorphic. But in fact, if I take any weight 12 forms and I take any two complex numbers, then the linear combination has a unique 0 up to this issue of multiplicity. Yeah.
That space there was spanned by two functions, which is E4.
Right, right. But take any, yeah, it's true. But, all right, I could take E4 cubed and E6 squared, but I could take any linear combination of those two that I wanted to make F12, and any other combination I wanted to make G12. In other words, the argument doesn't depend on what particular combination I'm going to choose, so I'm just making it take two generic weight 12 forms. It's true that space is just spanned by two weight 12 forms, but choose any combination you want. So this combination has a unique 0 up to this factor of a third or a half if the 0 happens to be at rho or I, but if I choose generic alpha and beta, then it won't be at one of those 2 points. And that just follows from that formula for the zeros, which tells me that the ord at P of f plus ord at infinity of f is equal to 1 for k over 12. And okay, there's this factor, but if I'm not at omega or I, then this goes away. And so this just tells me that there's a unique zero of order 1 at some point for any alpha and beta.
So just to understand, what you just wrote here is equivalent to saying that any element in M12 has a unique zero.
Right.
It seems like a fancy way of saying it.
Yeah. It's a fancy way of saying that. But the all right, so the reason I'm saying it in this slightly fancy way is that at that zero, the ratio of F12 to G12 is equal to alpha over beta. And so the space of alphas and betas, which are complex numbers, modulo the action alpha and beta goes to lambda alpha and lambda beta, for lambda a complex number which is not zero, defines complex projective space, which is often called the Riemann sphere. By that usual picture that you can map the complex plane to a sphere by projection. So what this is telling you is that this function gives me a map from the fundamental domain into the Riemann sphere. In other words, every point in the fundamental domain gets mapped to a unique point in the Riemann sphere by this ratio of two weight 12 functions. And you can see that you get mapped to unique points because if there were 2 points here that came from the same point here, you would have this ratio being equal for 2 different values of alpha and beta, and then you could subtract 2 functions and get a contradiction. So basically, this argument about the zeros and the ratio of 2 weight 12 functions tells you that that ratio gives you a map from the fundamental domain to the Riemann sphere. So in other words, what it's doing is it's taking this region here, and any ratio of weight 12 functions is mapping that to the Riemann sphere. So topologically, this is like a sphere. It has a sphere with these kind of, orbital fold points, and you have to add a point at infinity. But once you add that point in infinity, you're mapping every point in here to a point on the Riemann sphere. And we have chosen a particular way of doing that, J, but you could have done anything else. So the particular choice we made is one where the only pole is off at I infinity rather than someplace in the interior, but that's just a question of which points gets mapped to which points. So in other words, if you didn't like J, you could take some rational function of J over some other rational function of J, and that would give you another map, but just where you moved around what points got mapped to what points. So J is really a kind of fundamental object in terms of geometry, but it also has all sorts of other amazing connections to it. One of them is very dear to my heart, and I'm going to resist telling you too much, but there's an amazing connection between the modular function j of tau, where I subtract that 744, and the representation theory of the largest sporadic finite group, finite simple group. So, as you probably know, mathematicians like to classify things, and one of the things that they have classified to death is finite groups. So finite groups can be decomposed into smaller groups if they have normal subgroups by taking a quotient. And when you can't do that anymore and there are no more normal subgroups, you have something called a simple finite group. So if you can classify the simple finite groups, you can classify all finite groups. And the simple finite groups have a few infinite families and then 26 sporadic groups that don't fit into any families. And the largest of those sporadic things that don't fit into a family is the monster. And the order of this monster group is something like 10 to the 53. So it has, I don't know, some huge number of elements. And it has irreducible representations So in other words, just representations by some n by n matrices where matrix multiplication corresponds to group multiplication. And the irreducible representations of lowest dimension have dimension 1, because mapping every group element to 1 is always a representation. The next irreducible representation has dimension 196883, and the next one has dimension 21296,876. And if you look at your notes, if I write J of tau with these coefficients, then you find C of 1 is 196884. This is an observation due to John Mackay. And then the next coefficient is 21493,760, which is 21296,876 plus 196883 plus 1. And this idea, I think this next one was due to John Thompson, the suggestion that somehow there was a connection between the representation theory, that is, these are dimensions of irreducible representations of the monster, and the coefficients of a modular function was so outlandish when it was first observed that it was called moonshine, moonshine being something kind of fanciful or slightly illegal. And this is now understood, in a way, from the fact that there is a conformal field theory with central charge C equals 24 that has the monster as its symmetry group and this J function as its partition function. And that's a long, interesting story which was developed over many years. But it shows you that the theory of modular functions knows something about a whole other field of mathematics. It knows something about finite group theory, and even though a lot is now understood, partially explaining this, I think there's still a lot to be understood because it doesn't explain completely why all the things that are going on are going on. But anyway, I couldn't resist mentioning that.
Well, this relation has been
No, so essentially everything that you want that could be proved has been proved. So, yeah, 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 yeah. So it's been proved that all of these coefficients C of n can be decomposed into dimensions of irreducible representations with positive multiplicity. And much more has been proved as well. So you can, since the monster acts as a symmetry group, you can kind of do a twisting procedure where you twist by monster elements of the monster, and that leads to a whole other set of interesting functions. And there's a whole, I could give you many, many hours of lectures about what's going on here, but it would be in a completely different direction. But, and there are books that discuss this whole connection. Yeah.
Is there any gravity that is dual to monster system?
Very good question. So Ed Witten wrote a famous paper where he suggested that pure three-dimensional gravity in ADS3 was dual to this monster conformal field theory. But I think as people tried to follow that up, it was not really clear whether that was correct or not. I mean, he actually proposed a set of extremal conformal field theories that had central charges that were multiples of 24. I think the simplest thing to say is that there's been a lot of work on it, but there isn't a clear answer to that question. It would be very cool to be able to provide an answer. Because to get the monster out of some kind of three-dimensional theory of gravity, how cool would that be? I mean, that would really be amazing. I mean, if 3D gravity gives the monster, what does 4D gravity give? I mean, that's... All right. So, there's something else that I kind of debated whether I should tell you or not, but I perhaps gave in to my, my enjoyment of certain kinds of recreational mathematics and decided that I would tell you about it. And the justification is partly that it's kind of cute, but also that it's something that I hope to mention or use in a later lecture when we talk about elliptic genera and Jacobi forms and perhaps a little bit about black hole counting. And that is related to the theory of Hecke operators. So one of the things that you encounter if you start learning about modular forms at some point are an amazing set of results and conjectures due to the Indian mathematician Ramanujan, who was kind of a self-taught genius, and there's a famous story about him going to Cambridge and writing a letter to Harvey and all that. And I think there's actually a movie about his life coming out. But he loved modular forms and discovered many amazing things about them. And one of the modular forms that he discovered amazing things about was this weight 12 cusp form delta. So he computed the tau of n, I think up to n equals 30, something like that. He was a very fast calculator. And noticed a number of things. And in particular, he noticed that tau of p times q was equal to tau of p times tau of q if p and q are distinct primes. This is called a multiplicative relation. And, well, if you think about it, it's pretty cool because you can compute values of tau that are quite large if you know how to compute it, in a prime decomposition like this. And he also showed that if p is a prime, that tau of, or conjectured that tau of p squared is tau of p quantity squared minus p to the 11th. Which really looks peculiar, doesn't it? I mean, p to the 11th. So these relations, sorry? So I think both of these were conjectures that Ramanujan made. So I think these were conjectures due to Ramanujan. And then there was a proof, I think, well, at least the first one, I think the first proof was due to Mordell, but the proof that is now generally, that puts things like this into a broader framework is the result of Hecke, which is what I'm going to tell you about very briefly. And so I wouldn't, like I said, this is slightly technical, and I probably would have not done it, but then when I was thinking about what I wanted to do, these Hecke operators also play a role in trying to understand the elliptic genus calculations that go into black hole counting, going back to Strominger and Waffe, and so it seemed like a reasonable thing to do. And these results for delta can be understood using them. Okay, so in order to explain what this involves, let's consider, first of all, a lattice L and a sublattice L prime. The index of this sublattice in L can be thought of in a number of ways. One way is to think of it group theoretically. Because a lattice is an abelian group and a sublattice is a subgroup. And so in terms of that, the index is the order of L mod L prime. Or you can think of it geometrically, in which case it's the number of fundamental parallelograms of L in a fundamental parallelogram of L prime. And all right, here's a really simple example. Let's take L to be the lattice of the integers, L prime to be the lattice of twice the integers. So here's 0, 1, 2, 3, 4, minus 1, minus 2. So here are the solid dots, and then I'll put round dots on the elements of the lattice L prime. So here's a fundamental parallelogram, which is just a segment in this case for L prime, and it has two segments of L in it. So the index here is equal to 2. Or if we wanted a two-dimensional example, then I could do something like this. Etc. So here I have a lattice which is 4 times as big. So this is the lattice L. These round points are the lattice L prime, and the index is equal to 4. All right. So why am I talking about lattices? Well, modular forms of a given weight can be thought of really in 2 different ways, following the discussion that we had earlier. So they're either functions of tau, or we can think of them as functions of lattices (2D lattices). And remember that we wrote a general 2-dimensional lattice as spanned by 2 complex numbers, omega 1 and omega 2, and thought of that as a function, we have an integer span of omega 1 and omega 2 that defines a generic lattice for us. And we often decided that we were going to rescale by omega 2. Remember, we took omega 1, omega 2, and replaced this by 1 over omega 2 times omega 1 over omega 2, 1, and called this ratio tau. And we can kind of think of a modular form as either being a function of a lattice that obeys a particular scaling relation, or we can think of it as a function of the upper, on the upper half plane. And the relationship between the two is that here's a function of a lattice, here's a function of tau, and if f is a weight k modular form, then f is a function of a lattice such that when I rescale the lattice, the function rescales by the rescaling factor to the minus k. So in other words, there are 2 different ways of thinking of modular forms. They're either of weight k. They're either functions of a lattice that obeys this relation when I rescale the lattice, or they're functions of the upper half plane which have a particular transformation property. And those are just related by these 2 rescaling things. So the reason for mentioning this lattice point of view is that there's a very simple geometrical description of what a Hecke operator is, and it looks a little unnatural in terms of modular forms, but in terms of lattices it's very natural. So the Hecke operator Tm acting on a function of a lattice lambda is simply the sum over sublattices that have index m times the function evaluated on the sublattice. And if f obeys this homogeneous scaling relation, then it's kind of obvious that this quantity Tm f of lambda will also obey that scaling relation, just because f does. So with a little bit of work, going back and forth between these 2 points of view, you can translate this simple equation into a slightly more complicated looking equation. as follows. So if we have a modular form of weight k, you define the Hecke operator Tm acting on it to be a conventional factor, which is not really crucial to our argument. Something which I have to define for you. Where m sub m is the set of 2 by 2 integer matrices with determinant m. So why is this equivalent to that? Well, the basic point, other than up to some rescaling, is that if I think about my lattice and I do the kind of transformation that I was doing before, where I take integer linear combinations, this transformation with a, b, and c, d integers will generate from one lattice point another lattice point, because it's an integer linear combination of basis vectors. But if I take AD minus BC to not be 1, but to be m, then this gives me a point on an index m sublattice. So it gives me a new lattice point, but now instead of giving me a generic lattice point, it gives me a point on a sublattice of index m. And if you sum over all such matrices modulo the action of SL2Z, then that's equivalent to summing over all sublattices that have a fixed index in terms of functions of lattices. So it's possible to manipulate this a bit further. The representatives of 2 by 2 matrices with determinant m that are integers modulo those that are in SL2Z can be shown to be of the form A, B, 0, D, with A times D equals to m, that gives me determinant m, and 0 less than equal to B less than D. And if you want to show this, it's not too hard, but the standard way of doing it involves a theorem on what's called the Hermite normal form of integer matrices. So there's a change of basis that you can make that puts it in a normal form, and this is in the Hermite normal form. So you can show that. And once you've shown that, then you get a somewhat simpler formula for what the Hecke operator is. And this is the formula for a Hecke operator on modular forms of weight k that you will often find in the literature, but it's not very transparent where it comes from. It looks like a kind of weird cooked up thing, and it's not completely obvious from this definition that this will give you a modular form of the same weight. But it follows from translating this statement of lattices into a statement about modular forms, that it will give you a modular form of the same weight. So these Hecke operators map modular forms of weight k to modular forms of weight k. And I'm sorry that I'm skipping a few steps here, but in the interest of time, I kind of felt that I needed to. So one thing that's interesting to know is if you have a Fourier series for a modular form, which is a weight k modular form, what does the Fourier series of its action under this Hecke operator look like? And from that formula over there and a little bit of calculation, you can show that these coefficients are a sum over r dividing the greatest common divisor of m and n that are positive, r to the k minus 1 times a of m times n over r squared. So let me now, I've been a little sketchy in deriving that, I understand, but with some effort you could fill in the gaps. And now let me show you how one application of these Hecke operators to show and to prove these relations that were first observed by Ramanujan. So let's consider delta of tau. So a sub n are the coefficients in the Fourier expansion of f of tau. And you just take m times n and divide by r squared. And because r divides the greatest common denominator, divisor of these guys, this will be an integer, and you take the coefficient of that integer. Okay, so let's consider delta of tau, which has this form. And remember, tau of 1 was equal to 1, and we're not going to need the higher guys. Now, I guess there's something else that I haven't quite proved, but is true, which is that Tm takes cusp forms to cusp forms. I guess that follows from this, actually, since I don't get any b constant term. And so, in particular, if I act on delta of tau with this, it must be that delta of tau is an eigenfunction of the Hecke operator Tm because it's the unique weight 12 cusp form. So we can figure out what that eigenvalue is by looking at the coefficient of the first power of q in the action of the Hecke operator on Tm. That's equal to B1. B1 is the sum on R which divides m and 1, and is positive, times r, k is equal to 12, so this is r to the 11th, times a m over, so now the a's have become taus. So I now have tau of m over r squared. But the greatest common divisor of m and 1 is just 1, so this only has r equals 1. So this is simply tau of m. And the coefficient of q to the 1 in delta is 1, so it must be that lambda m is equal to tau of m. So in other words, the mth Hecke operator gives delta back again up to its coefficient tau of m, which is the coefficient of q to the m in delta. If we look at the coefficient of q prime in t p prime of delta, for q prime and p prime distinct primes, then what do we get? Well, from the right-hand side of this equation, the coefficient of q prime, of q to the q prime. I'm sorry, I have q prime is a prime, q is e to the 2 pi I tau. It's bad notation, but anyway. The coefficient of q to the q prime on the right-hand side under t prime of delta. So, all right, so I have, I'm being too fast. So on the right-hand side, the coefficient of q to the q prime is tau of p prime, tau of q prime. I just simply take the coefficient of q prime, q to the q prime, which is tau of q prime, and multiply it by tau of p prime. On the other hand, from the left-hand side, what is this? It's equal to bq prime, which from this formula over there is the sum on r dividing the greatest common divisor of p prime and q prime for positive r to the 11th, tau of p prime q prime over r squared. But again, p prime and q prime are distinct primes, so their greatest common divisor is 1. So the only term here is r equals 1. So this is tau of p prime times q prime. And QED, we've proved this multiplicative property. All right, I will leave as an exercise to you, for you, which again just uses this, and now you can see where the 11th power is coming from. 11 is 12 minus 1, which is not as famous a relation as 196884 is 196683 plus 1, but anyway. So show that tau of p squared is tau of p squared minus p to the 11th. So these Hecke operators play a role in, well, as far as I know, they play a very important role in more highbrow aspects of modular forms. And they act very naturally, as we've seen here, on cusp forms, mapping cusp forms to cusp forms. But in the early days of string theory, when there were lots of applications of modular forms, I don't think anybody knew or cared about Hecke operators. But it's turned out that they've played a role in later developments, because one of the things that occurs in the calculation of black hole entropy using D-brane configurations is the elliptic genus of certain symmetric powers of K3. You have branes wrapping and moving on a K3 surface, and it turns out that you need to analyze quantum mechanics on a kind of tensor symmetric product of these spaces, and calculations of the elliptic genus can naturally be formulated in terms of Hecke operators. So these Hecke operators have now turned into a tool that it can be useful for theoretical physicists to know about, which is why I've showed you this. But it also, I don't know, it's a beautiful example of how some very bizarre looking relations involving coefficients, and there are other ones besides these, can be understood by looking at, you know, this kind of additional mathematical structure. And in a way, this is really something that's almost familiar from quantum mechanics. You know, in quantum mechanics, whenever you have a Hamiltonian, you should always look at all the symmetries that commute with the Hamiltonian, because you use those to classify or to label states. And it turns out that these Hecke operators actually commute with each other. And when you have a bunch of operators that commute with each other, then you should use those to classify the objects that you have. And so if you have Hecke operators acting on modular forms, then it's a very natural thing to try to construct simultaneous eigenfunctions of the Hecke operators. So doing this is something that's familiar from quantum mechanics, except the symmetry here is a more, you know, not as physical a symmetry as, you know, rotations or parity or something like that. But the same kind of structure and idea applies. We have some vector space of objects, modular forms. We should look at the symmetries, and we should classify things under those symmetries. And that's what these Hecke operators are doing for us. All right, so I will end there and see you again next week, I guess. Questions? Yeah. Yeah, well, yeah, the monster CFT is chiral in that if you do it in bosonic string theory, the partition function is really J of tau squared. And what the mathematicians study as a vertex operator algebra is kind of the holomorphic part of this. But if you wanted to do it in conformal field theory language, then it's a theory for which the partition function completely holomorphically factorizes into a product of left and right movers.
So if there is some gravity rule, the right moving central vector should be 0?
Well, yes, possibly. I mean, if you wanted to get just the chiral part of this on the nose, then it would be natural to look at some kind of chiral 3D gravity. On the other hand, if you had a non-chiral theory that gave you this thing squared, I don't think you would be unhappy, because this theory actually has a symmetry, which is sometimes called the bi-monster, which is just two copies of the monster acting on the left and right movers, and a Z2 which exchanges them. So, you know, I mean, there's nothing wrong with getting the monster. If you like the monster once, you ought to be happy to get it twice. So it depends upon what you want to get, I guess.
So I mean that pure ADS gravity cannot go to monster CFT?
Just, well, you mean the chiral, just the purely chiral part?
Because it cannot be chiral.
Yeah, yeah. But you know, but you could have a theory which has the left, yeah, has the bi-monster as the symmetry, and I think that would be equally as amazing. Sure. Other questions?
These Hecke operators,
Yeah.
do they come up also when studying generalizations that higher rank groups?
You mean higher rank than SL2Z? I don't know. Yeah, I don't. What? You think they do? I wouldn't be surprised. I just didn't want to say yes or no because I don't know immediately whether what the answer is. Other questions?
The dimension of the monster group,
Yeah.
they have found some correlation with some physical quantities. It looks like they
Like what? Really?
bound to some.
Really? The only thing I've ever heard is people say, oh, it's rough, many elements in the monsters, there are protons in Jupiter, which doesn't sound like a very... But what kind of connection?
It's like a natural number that is a bound of something. It's the maximal finite group, if I understood that. That's the biggest.
I don't, yeah, maybe you could, if you could give me a little more detail about what the connection is. I don't know of such a thing. I mean, in Witten's proposal for the 3D gravity dual, you can use properties, you can study these coefficients and you can relate them to the entropy of black holes conjecturally, if there is such a dual. And the fact that the log of 196884 is roughly 4 pi is regarded as evidence for this, because there's a gravity computation of what the entropy should be of certain black holes, and then it should match this coefficient in the expansion of J, and this is, I don't know, true to within 10% or something like that. So, but this is only physical if you regard black holes in three-dimensional gravity as physical. I don't know of any other connection to the actual real world, but if there was one, it would be, I'd love to know about it. Other questions? Okay.